Space is vast. It's filled with wonders, from the twinkling stars that dot the night sky to the majestic galaxies that span across the cosmos. The universe is a treasure trove of marvels waiting to be discovered. But none are as captivating as black holes. These enigmatic entities have fascinated scientists and stargazers alike for decades. These celestial objects are shrouded in mystery. Their very nature challenges our understanding of physics and the fabric of reality itself. They are a testament to the immense power of gravity. The force that binds the universe together is at its most extreme around these cosmic giants. Black holes challenge our understanding of the universe. They push the boundaries of what we know and force us to rethink the laws of physics. Imagine a place where gravity reigns supreme. A place where the pull of gravity is so strong that nothing, not even light, can escape its grasp. A place where even light cannot escape. This is the realm of the black hole, a region where the known laws of physics cease to apply. This is the defining characteristic of a black hole, a region of space-time so dense that its gravitational pull traps everything within its grasp. A region of space-time so dense that its gravitational pull traps everything within its grasp. The event horizon marks the boundary beyond which nothing can return. The very idea of a black hole sparks curiosity and fear. It is a cosmic enigma that beckons us to explore its depths, yet warns us of its dangers. It's a cosmic abyss, a point of no return. Once crossed, there is no escape from the black hole's grasp. Yet, their existence is not science fiction. Black holes are real. They are out there, lurking in the depths of our universe, waiting to be discovered. They lurk in the depths of our universe, hidden among the stars. They silently influence the cosmos around them. Understanding these enigmatic objects requires a journey into the heart of astrophysics. It demands a deep dive into the theories and principles that govern our universe. It demands we confront the limits of our knowledge and embrace the unknown. Only then can we hope to unravel the mysteries of these cosmic titans. Black holes are not cosmic vacuum cleaners. Contrary to popular belief, they don't roam the universe, indiscriminately devouring everything in their path. Instead, they are fascinating and complex phenomena that arise from the life cycles of massive stars. They don't wander the universe sucking up everything in sight. Rather, black holes are born from the dramatic and violent deaths of massive stars, which are some of the most powerful and awe-inspiring events in the cosmos. Instead, they're born from the death throes of massive stars. Stars are cosmic furnaces. These stellar giants spend most of their lives fusing hydrogen into helium in their cores, a process that releases an immense amount of energy. They fuse hydrogen into helium in their cores, releasing tremendous energy. This energy is what powers the star and creates an outward pressure that counteracts the inward pull of gravity. This energy creates outward pressure. The balance between this outward pressure and the inward pull of gravity is what keeps a star stable for millions or even billions of years. It counteracts the inward pull of gravity. This delicate equilibrium is essential for the star's stability, allowing it to shine brightly in the cosmos. This balance is what keeps a star stable. However, this delicate balance cannot last forever. Over time, the star's core will begin to run out of hydrogen fuel. However, this delicate balance cannot last forever. As the star ages, it eventually exhausts its nuclear fuel. When this happens, the star can no longer sustain the fusion reactions that generate the outward pressure needed to counteract gravity. As a star ages, it eventually exhausts its nuclear fuel. Without the outward pressure from fusion, gravity takes over, leading to the star's inevitable collapse. Without the outward pressure from fusion, gravity takes over. For massive stars, this results in a spectacular collapse, an event that is both catastrophic and beautiful. For massive stars, This results in a spectacular collapse. The star's core collapses in on itself, creating a highly dense and compact object. The star's core collapses in on itself. This triggers a supernova explosion, one of the most energetic events in the universe. This triggers a supernova explosion. The outer layers of the star are blasted into space, creating a brilliant and short-lived spectacle. The outer layers of the star are blasted into space. What remains is a core so dense that it collapses into a singularity, the heart of a black hole. What remains is a core so dense that it collapses into a singularity, the heart of a black hole. This singularity is the point of infinite density, where the laws of physics as we know them cease to exist. The boundary around a black hole is the event horizon. This is the point of no return. Cross the event horizon and there's no coming back. Not even light can escape the immense gravity beyond this point. Imagine falling into a black hole. As you approach the event horizon, time itself would seem to slow down. This is due to the intense gravity warping the fabric of space-time. You would witness the universe around you distort. Light from distant stars would bend and smear. This is gravitational lensing in its most extreme form. As you fall closer to the singularity, you would experience spaghettification. The gravitational pull on your feet would be much stronger than on your head. This would stretch you out like spaghetti. Ultimately, you would be ripped apart. Section 4. Beyond the Veil. Portals to other realms? Black holes are shrouded in mystery. They push the boundaries of our understanding. Some theories suggest that black holes could be gateways to other universes. These theories stem from the idea that the singularity at the center of a black hole represents a breakdown of our current laws of physics. What happens inside a singularity is anyone's guess. Could it be a bridge to another universe? A white hole, spewing out matter and energy? Or something even more exotic that we can't even comprehend? While these ideas are intriguing, they remain highly speculative. We lack the observational data to confirm or refute them. The true nature of black holes, particularly what lies beyond the event horizon, remains one of the greatest mysteries of modern science. Section 5. Galactic Mysteries Unveiling Sagittarius A*. Our own Milky Way galaxy harbours a supermassive black hole at its centre. This behemoth is known as Sagittarius A*. It's a gravitational giant with a mass millions of times that of our Sun. Astronomers have been studying Sagittarius A* for decades. By observing the orbits of stars around it, they have been able to infer its presence and estimate its mass. The Event Horizon Telescope, a global network of telescopes, captured the first ever image of Sagittarius A* in 2022. This groundbreaking image provided direct evidence of its existence and gave us a glimpse into the environment around this supermassive black hole. Section 6. The ultimate fate, lost in the singularity. What happens to objects that fall into a black hole? This question has puzzled scientists and astronomers for decades. Black holes, with their immense gravitational pull, are one of the most mysterious and fascinating phenomena in the universe. Do they simply cease to exist, crushed out of existence by the singularity? The intense gravitational forces at the core of a black hole, known as spaghettification, stretch and compress objects beyond recognition. Or is there something more to their fate? Could there be unknown phenomena at play, altering our understanding of physics and the universe itself? Some theories suggest that information about an object is not lost when it enters a black hole. This idea challenges the traditional notion that black holes are cosmic vacuum cleaners, erasing everything they consume. Instead, it might be encoded in some form on the event horizon. This concept has led to the development of the holographic principle, which posits that all the information contained in a three-dimensional space can be represented on a two-dimensional surface. This is known as the holographic principle. It suggests that the universe itself might be a hologram, with all the information about our three-dimensional world encoded on a distant two-dimensional surface. Others propose that black holes might eventually evaporate through a process called Hawking radiation. This radiation, named after physicist Stephen Hawking, is a theoretical consequence of quantum mechanics. This radiation, named after physicist Stephen Hawking, is a theoretical consequence of quantum mechanics. It suggests that black holes are not entirely black, but emit small amounts of thermal radiation. The fate of objects entering black holes, much like the nature of the singularity itself, remains an open question. The singularity, a point of infinite density, defies our current understanding of physics. It's a question that continues to drive scientific inquiry and capture the imagination. As we develop new technologies and theories, we inch closer to unraveling the mysteries of black holes and the singularity, pushing the boundaries of our knowledge and understanding of the universe.